In this lesson, we will discuss how to find formal charges in bond line drawings, how to find lone pairs in those bond line drawings, and also how to represent the three-dimensionality of structures when we are drawing bond line drawings or skeletal drawings. So with carbon, remember that carbon is tetravalent. It likes to form four bonds, or preferentially forms four bonds. And so when you find a carbon that does have four bonds to it, it's going to have a formal charge of zero. Typically, those bonds will either be to other carbon atoms, or um, if the number of carbon bonds shown is less than four, the remainder go to hydrogens. So when you have a carbocation, which is a carbon that's going to have a positive charge, um, it will only have a total of three bonds to it. That fourth orbital will be empty, and it'll be a p orbital. So the three bonds that are formed will actually be sp2 hybrid orbitals. So depending on where that carbocation is located will inform how many hydrogens we could expect. So for instance, in the far left structure that we see here, that has three carbon-carbon bonds already, plus that empty orbital for the positive charge, means that there's not going to be any hydrogens on that carbon in that location. If we see a carbocation that is only bonded to two carbons, that means that there's one bond left, and that would be to a hydrogen. If your carbocation's in a terminal position, you've got the one bond to the carbon, you've got the empty orbital for the formal charge, and that means that you're going to have two hydrogens present. A carbanion is when you've got three bonds to the carbon and then a lone pair, so you don't have any empty orbitals here. And that additional electron is what provides carbon with that formal charge of -1. In general, whether it's carbon or any other atoms, we need to be able to identify those charges because that affects the stability and the reactivity of the molecules. And so when we look at a structure, we want to be able to do a quick accounting, a quick scan, and look for the characteristic valencies. So like carbon is tetravalent, it forms four bonds. Oxygen is usually divalent, forming two bonds for a formal charge of zero. Nitrogen is trivalent. And so as we look at this structure, we can see that, right here with oxygen has a total of three bonds to it. That's not typical, okay, for a formal charge of zero. So if we do the math, and remember to calculate formal charge, you start with the valence electrons, which is 6 for oxygen. Then you subtract the number of lone pair electrons, which in this case is 2, so that takes us to 4. And then you take the total number of bonding electrons. So we've got 2, 4, 6, and you divide that by 2, so that gives us 3. 4 minus 3 leaves us with a positive 1, so we actually have a +1 charge on this oxygen. All right, if we look at this oxygen, 2 bonds, 2 lone pairs. That's typical for oxygen. Okay, so no formal charge there. But on this oxygen, we see 1 bond and 3 lone pairs. So in this case, oxygen would have a -1 formal charge. Nitrogen, okay, nitrogen is typically trivalent, but here it's forming 4 bonds, and so this is going to be a location where we have a +1 charge. Here, nitrogen's got 3 bonds and a lone pair, so that's typical, so we don't need to show any charge there. And even sulfur, you might think, well, sulfur's looking pretty busy there. But sulfur's valence electrons are 6, minus 2 lone pair electrons. That makes 4 by 2, which is 4, which brings sulfur to having a formal charge of 0. So there's actually nothing that we need to show there. While we always have to show formal charges, lone pairs are optional, and typically they're not going to be shown. Lone pairs, or where they would be absent, is going to be a key as well. So when we draw an oxygen with a formal -1 charge, formal charge of -1, it can be drawn either one of these, but it can make things a little busier in terms of the structure itself. And again, because of that, third lone pair means you've got an extra electron, which is what leads to the -1 charge. All right. So when we see oxygen, okay, that has a -1 charge, we know that there's going to be 3 lone pairs on it and only 1 bond. No charge, no formal charge, two bonds, two lone pairs. And if it's oxygen with a positive charge, that means it's connected to three atoms and only one lone pair present on it. If we take a look at these structures, okay, and for each of the oxygens, identify and then draw in how many lone pairs there's going to be. So if you want to take a moment, pause the video, try it on your own, and then restart the video to check your answers. So if we take a look, okay, in this first one, we see oxygen is double bonded to the carbon, and there's no other bonds to that oxygen. So we know that with two bonds on an oxygen, there's going to be two lone pairs. We draw them in kind of on an angle like that to represent the trigonal planar nature of the sp2 hybridization that oxygen has there because of that pi bond. If we look at the next one, again, we see an oxygen here with two bonds. So we know there's two lone pairs on this one, as well as this oxygen has two bonds to it. And so there are two lone pairs on that oxygen. Looking at the last one, again, C double bond O, that carbonyl group. We know there's going to be two lone pairs on it. And this oxygen, which is connected to hydrogen, there's two bonds there. So once again, two lone pairs. Here are some more examples. So if you want to pause, try these, and then restart the video to check your answers. Okay, so in this first one, the carbonyl oxygen, all right, is a familiar one to us, hopefully by now. There's going to be two electron pairs on that. But here we have a -1 formal charge on the oxygen, which means when we've got one bond and a -1 formal charge, that means we're going to have three lone pairs. All right, in this structure here, we see oxygen bonded to two other carbons, no other bonds to the oxygen, so that means there's going to be two lone pairs on that oxygen. And in this last one, oxygen's carrying a +1 formal charge, and there are three bonds to it, so that means that there's only going to be one lone pair on that oxygen. We can do the same sort of thing for nitrogen. Whenever you have a nitrogen that has a -1 charge, you know that there's going to be two bonds and two lone pairs present. Nitrogen typically is trivalent, so if there are three bonds to it, that means there's only one lone pair. And if you have a nitrogen that is really busy, so to speak, and has four bonds to it, then there's no possibility of having lone pairs on that nitrogen because nitrogen is one of those elements that must have no more than 8 electrons total. So once again, if you try these examples here, pause the video, give them a shot on your own, and then restart to check your answers. So in this first one, we see nitrogen has 1, 2, 3 bonds to it, and there's no formal charge shown on it, so that means that there is one lone pair of electrons on that nitrogen. In this one, again, three atoms bonded to that nitrogen, no formal charge shown, so there is one lone pair on that nitrogen. In the last one, nitrogen has four bonds to it, and it has a +1 charge. So we know that with a +1 formal charge and four bonds, that means there are no lone pairs on that last structure. Pause the video, try these on your own, and then restart to check your answers. In this first structure, we've got nitrogen with two bonds to it and a -1 formal charge. So that -1 formal charge is telling us that we have an extra lone pair beyond what nitrogen typically takes on. So you have two lone pairs. In this structure, we have nitrogen showing a +1 formal charge, and there are four bonds to it. So that would not have any lone pairs on it. And in this last one, three bonds to the nitrogen, no formal charge shown. So there is an implied lone pair on that nitrogen. Now, our molecules aren't just flat. When we draw a bond line structure, it's easy to think of them as a flat planar structure. And some of them may in fact be, but the large majority of them, if there's sp3 hybridization, that's got a tetrahedral shape around it. It's going to be three-dimensional. So how do we show that three-dimensionality? The way that we typically do it is by using wedged bonds. They could be solid wedges or they could be dashed wedges. And so when we look at this first one here, it's an acyclic hydrocarbon, just meaning it's basically a chain of carbons. Whenever you see a solid wedge, that's indicating that the atom that's attached to that solid wedge is coming out of the plane of the carbons. Okay, so the plane that the carbon chain is in, which is basically the screen or the paper, the page, that chlorine atom right there would be popping out towards us. The one with the dashed wedge would be going behind the plane of the paper, so it would be angled away from us. We can do that with cyclic, okay, where there's one ring of carbon atoms. Um, but sometimes we can have more complex systems where you have multiple rings or a bicyclic system. So, this is like a top-down view, and you can see this one right here where it's showing two wedges. So there's a carbon right here at the apex of that. And if you kind of think of that like a handle, okay, if these 1, 2, 3, 4, 5, 6, these six form like a platter, okay, this would be like the handle that you could then pick it up by. That's just a way to kind of visualize that. As we look at some of these other projections, this one here on the far right, that's kind of like if we took that platter and turned it on its side. So now we can see that handle sticking up. You'll notice in this, we don't really use wedges, but we use uh, different angles, okay, for the axial and the equatorial positions to show how those groups are sticking out. Then you have Hayworth projections, which again take that ring and kind of tilt it on its side, and wedge structure. The groups coming off of those carbons in a Hayworth projection are just usually drawn vertical and above and below. And then you have Fischer projections, which are only useful for non-cyclic or acyclic compounds. And typically what you have there is the carbon backbone, instead of being drawn in a zigzag formation, is drawn vertically in a straight line formation. And then any of your heteroatom groups are typically shown explicitly. And even sometimes the hydrogens, as you can see here. Understanding the shape, the three-dimensional shape of these molecules allows us to be able to understand how they're going to react chemically with each other, but also a lot of the organic chemicals are going to have biological functions as well. So being able to see where these unique functional group structures are located in relation to the carbon groups and the hybridization and the geometry is going to allow us to be able to understand those biological functions better.